Till now, what we have discussed is about the composites application and the process. Now we are discussing about the characteristics and important properties theoretically and as well as numerically. Now, first of all, what we will discuss in this session is the characterization of the composite. Characterization of the composite refers to the broad in the general process by which the composite material structural and as well as the properties are examined and as well as measured in order to ensure that the material meets the application and as well as the performance of the requirement. Today, there are variety of the characterization techniques are available for the different types of composite materials. Some of the different methods we are discussing in this session. The first one, microscopic and as well as metallographic analysis. The microscopic analysis is used to investigate the following points are the quantitative phase analysis determining the size and distribution and orientation of the fiber, and also the particle identifying the characteristics and the defects like the voids, debonding and as well as the fiber bending, etc. The degree of bonding between the matrix and as well as the reinforcement or the between the layers, and the chemical analysis and also the distribution of the particles, which is nothing but the reinforcement is measured by using either by SEM, which is nothing but a scanning electron microscope. The another one is a TM, transmission electronic microscope or transmission electron microscope. The third one is EDX, energy dispersive X-ray spectroscopy. These are the different techniques normally what we are using it to quantify the material distribution and also the defects in the composite. The thermal analysis. Thermal analysis is an ideal characteristics material property like the glass transition, the content, decomposition, behavior, heat capacity, thermal conductivity, elasticity, viscosity, and as well as a damping behavior are measured as a function of temperature and as well as the time. Thermo gravimetric analysis, differential scanning calorimetry, and dynamic mechanical thermo analysis are the common employed in characterizing of the composite material. The TGA, the thermogravimetric analysis, is used to measure the degradation and decomposition of the material. DSC, which is nothing but the differential scanning calorimeter, is used to measure the melting point and as well as a phase transition of the composite material. Dynamic mechanical thermal analysis DMA is used to investigate the elastic modulus, viscosity and as well as the damping characteristics of the composite material. NDT. NDT is a normal method which can be adopted either for the metallic material or it may be non-metallic material, or even composites also the same method is adopted. The NDT is a primarily intended to detect the surface and as well as subsurface defects of the composite material. These techniques are based on the different methodologies. Few of them are listed as follows. The ultrasonic testing is used to monitor the delaminations, defects, flaws along the axis, and as well as the size, shape, location, the fiber matrix damage, and as well as discontinuity. Thermography test measures the effect of the thermal change, delamination, and as well as contamination, like either it may be the moisture or it may be a solvent or some other defects. The radiographic testing is used to detect the particle size, the density, charges, uh, locate delamination, or it may be the voids, or it may be the porosity, or it may be the moisture or the inclusions, etc. Other techniques includes electromagnetic testing, spectrography, acoustic emission, optical inspection, etc. The constitutive relation of the composite. The constitutive relation of the composite is primarily essential to identify the properties of the material theoretically. The properties of the composite material depends upon the properties of its individual constituents and their distribution, either it may be in the physically and as well as chemically. Although the properties of the composite materials can be accurately determined through the experimental measurements, certain laminations or certain limitations do exist. As such, the theoretical and as well as the empirical methods have been formulated to approximate the estimation of the various properties. Especially in this method, the results what we are obtaining is of something like an approximation method. It's not the exact method. The four elastic moduli are the longitudinal Young's modulus, transverse Young's modulus, Poisson's ratio, and as well as the shear modulus are discussed in the present section. The next topic is nothing but the role of mixture. The role of mixture for the evaluation of the four elastic moduli is most important, which is nothing but the mathematical expressions which indicates the some properties of the composite in terms of the quantity and arrangement and its individual constituents. The rule of mixture is based on the number of simplifying assumptions as listed below. As we know that any material, while designing it or while calculation, we have to go some assumption. Without doing assumption, it is very difficult to go for a theoretical evaluation. The reinforcing fiber is a uniform in its properties and diameter all along the length. Especially in this first assumption, as we know that the property it's not same throughout the length of the fiber, and also the diameter is also not even throughout the length because of some defects. There may be some variations, but even then also we are assuming it as a uniform. The second one is the fiber distribution throughout the composite is continuous and as well as a parallel. While fabricating the composite may undergo some load, or it may be a pressure, or it may be some deformations. In that case, there may be a breakage of the fiber. In that case, the continuous property that it cannot be maintained. Even then also, if there is a discontinuity, we are assuming that as a continuous and also the parallel. The fiber and as well as a matrix behave as a linear elastic material and obeys the Hooke's law. As we know that Hooke's law is stress is directly proportional to strain within the elastic limit. But if you take an example of these type of material, as these material, like either it may be matrix material and as well as a fiber material, these two are having a different Young's modulus and as well as a elasticity, and also where the Hooke's law will also vary. But here in this case, we are assuming that the fiber and as well as the matrix behaves like a linear elastic material which obeying the Hooke's law. The composite is free from voids. Any material while under processing, there may be a chances of some defects, but here while doing the calculation, we are assuming that it has a defectless component. The fifth one is applied load is either parallel or normal to the fiber direction. Even if there is a deformation in the fiber, or dislocation, or maybe the orientation has been changed, even the loading condition, we are assuming this as the either it may be parallel and as well as normal. Further, based on these assumption, we will go some empirical formulas and as well as derivations. The rule of mixture for evaluating longitudinal Young's modulus. Consider a composite with a single fiber subjected to a tensile load P along the longitudinal axis of the fiber as shown in the figure. In the schematic diagram shown below, here there are two matrix layers are there. In between one a fiber layer. As we know that between the two fiber layer, a matrix layer it will be there, but the loading condition it is uniform even for the matrix and as well as the fiber. The total load acting on the composite is shared equally by the fiber and as well as the matrix. For that reason, the total load on the composite is equal to P suffix F plus P suffix M, which is nothing but the load on the fiber and also the load on the matrix. where the subscripts indicates C indicates the composite, F indicates the fiber, M indicates the matrix. As you know that stress sigma is equal to P by A, or the stress is equal to load by area. Now the PC, it can be written as sigma suffix C A suffix C, which is equal to sigma suffix F A suffix F and also sigma suffix M and A suffix M. With respect to the stress, the sigma suffix C is equal to sigma suffix F within the bracket A suffix F by A suffix C plus sigma suffix M within the bracket AM by AC. Sigma C is equal to sigma F VF plus sigma M VM, where V is equal to V suffix F is equal to AF by AC and VM is equal to AM by AC, which is nothing but the volume fraction of the fiber and as well as the volume fraction of the matrix. With respect to the Young's modulus, we know that stress by strain is equal to Young's modulus. The equation 2, it can be written as E suffix C epsilon suffix C is equal to E suffix F epsilon suffix F V suffix F plus EM epsilon M VM. Under the assumption that the fiber is rigidly bonded to the matrix, no stiffness occurs at the interface and such that both the fiber and as well as the matrix is experiencing a uniform strain, then sigma epsilon F is equal to epsilon M. The strain in the composite is equal to strain in the fiber and also the strain in the matrix. Therefore, the equation 3 can be written as E suffix C is equal to E suffix F VF plus VM. This is a generalized equation with respect to the Young's modulus of the composite. Now the following equation also applicable for the composite material, as we know that the ratio of the load is shared between the fiber and as well as a matrix. PF by PM is equal to EF VM by EM VM. The fraction of load carried by the fiber, PF by PC, is equal to EF VF by EF VF plus EM VM. In the same way, the fraction load carried by the matrix is equal to PM by PC is equal to EM VM by EF VF plus EM VM.